After watching this video lecture, students are going to be able to identify the species present and calculate pH at various points of a strong-weak titration. Students will also be able to compare and contrast the characteristics of strong-strong versus strong-weak titration curves. So some considerations that you need to have or kind of keep in your mind as you're working with strong-weak titrations. So in the example of a weak acid being titrated with a strong base, before you've reached your equivalence point, Ka and ice tables are going to need to be used in order to calculate your H plus concentration. And so basically these are going to be a series of weak acid calculations. And also you need to consider that the concentration of the species present is going to be equal to the number of moles of species remaining divided by the total liters of solution. So remember, since this is a weak acid problem, you are going to have to consider the conjugate base that gets produced. At equivalence point for strong-weak titrations, your equivalence point for this specific example is going to be greater than 7, and that's because the conjugate base ion is present. And lastly, after the equivalence point, we're going to kind of go back to what we've seen in the past, and the moles of hydroxide ion divided by the total volume of the solution will give you the concentration of the hydroxide ion at that point and allow you to calculate your pOH and subsequently pH. Now, the opposite of what we've just discussed here is going to be true if the titration setup is one in which a unknown weak base is being titrated with a strong acid. And so these are the considerations to have as we proceed. Okay, so depending on the strong-weak titration that you're considering, please remember that your weak acid or your weak base that's present in solution is going to react with the titrant to produce either a conjugate base or a conjugate acid. And remember that we have to consider the changes that occur based off the conjugates that are produced from weak acids and bases. And so what we're going to do here is we're going to look at a case study of basically the titration of 50 milliliters of a 0.1 molar acetic acid solution with a 0.10 molar sodium hydroxide solution. We're going to look at various points along the curve, but please, guys, make sure that you are understanding that, of course, we could do any other points within this titration process. Okay, so we're going to go ahead and look at point A here, okay, or the initial point, before actually the titration has begun. So in this case, guys, we've added 0 milliliters of our sodium hydroxide. And if you look at the pH here, notice that the pH is around 3, which is a little bit higher than what we saw when we were doing the strong examples. In this case, because we have a weak acid down at the bottom in that Erlenmeyer, the ionization extent is going to be smaller, so H plus concentration is lower, and your pH is subsequently higher. Okay, so really what this problem is going to be is basically a weak acid problem. Why? Because sodium hydroxide is not going to be changing the concentration of our acetic acid species. Okay, so pH is going to be determined by the ionization products associated with acetic acid. In this problem, we're going to need Ka and an ice table. Okay. So as you can see here, I've set up my ice table. I've set up it based on the ionization of acetic acid to H plus and the acetate ion. My initial concentration is 0.10 molar and 0 respectively. The changes correspond to X here, and my equilibrium values, of course, are as seen here. Now, we're going to now plug these into the equilibrium expression for this ionization process. This is what we end up here, okay? And so what we now need to consider, of course, like we have in the past, is that since our Ka is small, we can probably drop X. So if we go ahead and we drop X, and we subsequently solve for our X value, we end up with the following X value. Okay, and that X value is going to correspond to our H plus concentration. And our H plus concentration can be plugged into our pH equation to solve for pH. So in this case, we're going to have this set up, which gives us a pH value equal to 2.87. Okay, and so this is the starting point in our titration curve, our point A. And basically, once we start to add our sodium hydroxide, we're going to move away from this pH, and that pH is going to continue to increase. And that's going to be due to the interaction between our acetic acid and the hydroxide, subsequently decreasing the amount of the acid we have to ionize in solution. Okay, so we'll look at this as we progress through. Okay, so we're going to go to point B. We're a little farther along the process. Okay, so at this point we were saying we're adding 25 milliliters of our sodium hydroxide. So the species that would be present in solution before any reactions would occur would be our acetic acid, our water, our hydroxide ion, and sodium ion. Okay, and of course we know that our acetic acid and our hydroxide ion are going to interact with each other to form the acetate ion and H2O. Okay, now before we can plug this in and basically do a weak acid calculation problem with our ice table and equilibrium expression, we first need to figure out how much acetic acid is in solution after some of it has reacted with the sodium hydroxide. So we basically need to figure out how many moles of each species of our acid and our base are present initially, and then what remains after reaction. Okay, so now that we've set up the reaction that's going to occur between the acid and the sodium hydroxide base, we need to figure out what the before values are going to be for both of these species. Okay, so we know that we started with 50 milliliters of our acetic acid, and that it has a 0.10 molar concentration, so we're going to go ahead and multiply those values. And we've added 25 mils of our 0.10 molar sodium hydroxide, so we're going to multiply those to get our molar amounts. So we're going to do those calculations now. So now you can see how I calculated my moles of acetic acid and my moles of hydroxide ion. I've plugged them into the before values. Now these two are going to react with each other in a one-to-one fashion. Okay, so basically one equivalent of hydroxide will react with one equivalent of acetic acid to give me one equivalent of my acetate ion. Okay, so my after moles are going to look like this. Now these are the values of all of our species after the acetic acid and hydroxide ion have reacted with one another. So basically I have no more hydroxide present, I have half the quantity of acetic acid that I had before, and now I have acetate ion present. So we're going to go ahead and take these mole values and convert them to molarity and plug them into the ice table for the ionization of the acetic acid. Okay, so go ahead and set that up. Okay, so we've set up the first part of our ice table here. We have taken our moles of our acetic acid and our acetate ion, and we divided by the new total volume of the solution. Remember, we had 50 milliliters of acetate ion originally, and then we added 25 milliliters of sodium hydroxide to that container. So now the total volume in that container is 75 milliliters, or 0.075 liters. Divide these numbers out to get our new molarities for our initial acetic acid and acetate ion. Okay, now obviously our acetic acid is going to decrease in concentration, and both our H plus and acetate ion should increase. Okay, so we're going to finish up this ice table. So now that we have set up the rest of our ice table, we have our equilibrium concentration values, and we're going to plug those into our equilibrium expression for this ionization process here. And so this is the equilibrium expression that we get with all of our plugged in values. Now remember, Ka is really small, so we're going to assume that X is really small for both the top and bottom values. That would subsequently leave us with 0.033 divided by 0.033, so those would cancel as well. So at this point in the equilibrium expression, X is going to be equal to 1.8 times 10 to the negative fifth. Okay, and if we take the pH of that, we're going to get 4.74. So our pH has increased significantly since the last edition that we looked at. Now, something I want to also point out to you guys, since the values of our acid and the conjugate are equal, we're at what's known as the half equivalence point. And at this point, guys, when you reach that half equivalence point for weak acid, the pH is going to be equal to your pKa value. And if you want to relate that to Henderson-Hasselbalch, you guys can go ahead and look at that and see how that works out. But basically, this is your half equivalence point, so we're halfway to said equivalence point. So we're going to go ahead and continue. We're going to look at our next calculation. So again, we have the same kind of setup. We're still adding sodium hydroxide to acetic acid. So we first need to figure out how much acetic acid remains after we've added our 50 milliliters of sodium hydroxide. So the same procedures as last time. I'm going to go ahead and set those up here. Okay, so if we go ahead and we take our 0.1 molar concentrations and multiply them by the 50 milliliters of each of the acid and the base that are in the container, we end up with 5.0 times 10 to the negative third moles of both our acid and the base that had been added. So when those react with one another, we're going to get the following, which as you can see, because these react in a one-to-one fashion, we end up with no acetic acid, we end up with no hydroxide ion, and what we end up with here is 5.0 times 10 to the negative third moles of the acetate ion. So the conjugate base is the only active or important species that is present in solution at this point. Okay, so guys, what we have reached here is what's known as the equivalence point, and because the amount of moles of acid and the amount of moles of base that have been added are equal to one another. Now, in this situation, if this was a strong titration, we would ignore the products that are produced because it would just be a neutral salt and water. But because of the fact that the conjugate that's produced can behave as a base, that species has to be analyzed with respect to how it will react with water. Okay, so we need to calculate now the pH of the solution based on having this much of the acetate ion present. So again, this is just going to be another ice table problem. However, instead of dealing with the acid, since it no longer exists, we're going to deal with its conjugate. Okay, so let's go ahead and set that up. So we have our equation here. We have our base, our conjugate base that's been produced. It's going to react with water to produce its conjugate acid and hydroxide ion. We expect here to have a basic solution, and so our pH at our equivalence point should be higher than 7. Okay, so what we need to do now is, because this is a basic process, we are going to need a Kb value associated with this specific feature or this specific species. Okay, so we're going to get our Kb from the relationship between Kw and our known Ka. So we're going to go ahead and set that up, and it's going to give us the following. Okay, and this is the value that we're going to use for our equilibrium expression. So now let's go ahead and move on to setting up our ice table. Now remember, when we're plugging values into the ice tables, we actually need concentration values, so I'm going to need to change this mole amount into concentration. So in order to calculate our concentration, we're going to do the following. So we're going to divide our number of moles of acetate ion by our total volume. Remember, we've added 50 milliliters of sodium hydroxide to the 50 milliliters of acetic acid to give us a total of 100 mils, or 0.100 liters. Divide these values, and that gives us a concentration of 0.050 molar. Okay, and so our initial values for all the other species will be as follows. So we've gone ahead and plugged this into our equilibrium expression, our equilibrium concentrations, as we see here. Now, just like any other weak base problem, we're going to see if we can drop x. Okay, so we're going to go ahead and we're going to drop the x on, like we would do for values that have small ka's or small kb's. And then we are going to go ahead and solve for x. And so the x value we're going to get from this is going to be x equals 5.267 times 10 to the negative 6th. Okay, so this is our x value. Now, our x value for this process is going to correspond to the hydroxide ion concentration. So I cannot directly calculate pH here. I first need to do pOH and then solve for pH. Okay, so we're going to go ahead and plug this in because this is equal again to the hydroxide ion concentration. And that's going to give us a pOH of 5.28, and then if we subtract that from 14, that's going to give us our pH, which is going to be equal to 8.72. Okay, so at this point, guys, we are at our equivalence point. Notice our equivalence point here is higher than if this was a strong titration. In this particular case, since we're adding base, and we are producing a conjugate base. Those conjugate bases from the weak acids behave as bases in solution and cause this to be higher than it would be for a strong situation. Okay, so now that we have reached the equivalence point, our next addition is going to be quite different. All right, so at this point, we have now added 60 milliliters of 0.10 molar sodium hydroxide. We saw in the previous example that we had reached our equivalence point. So we know that as we continue past the equivalence point, there aren't going to be really any acetic acid molecules present. Okay, so the pH change that we're going to see for the remainder of the addition of sodium hydroxide is going to be based mainly on the presence of the hydroxide ion. Okay, so I'm going to show you guys that the acetic acid no longer exists, and in fact hydroxide ion is the species that's going to be determining pH. Okay, so if we go ahead and we calculate the mole quantities, we end up with 5.0 times 10 to the negative third moles of acetic acid and 6.0 times 10 to the negative third moles of hydroxide ion. Okay, and we can see those calculations here. So when these react in a one-to-one fashion, notice there's more hydroxide than acetic acid. Okay, so when we go ahead and those react, we produce the following. So what we end up producing, obviously, or leaving behind, is a fair quantity of hydroxide and our acetate ion. Now, the acetate ion that's been produced obviously is not going to cause as large of a change in the pH as the hydroxide ion, so we subsequently ignore the acetate ion from this point on. So basically the hydroxide ion here, so in this context, all I really care about is the concentration of the hydroxide ion, since it's the main determining factor of my pH. Okay, so I'm going to calculate that by taking the moles of my hydroxide ion present and dividing by the total number of liters present. Okay, so I've added 60 mils of sodium hydroxide, 50 mils of acetic acid solution. So we're going to have 1.110 liters of solution. So we go ahead and we divide those in, and what we end up with is a concentration of the following value. Okay, and this is our concentration of our hydroxide ion. Now, if we take the negative log of this, we'll get our pOH, which is going to be equal to 2.04. And our pH, if we subtract it from 14, is going to give us 11.96 as our pH value. Now notice that's a pretty big jump from the equivalence point that we just saw, and that's because, you know, those hydroxide ion concentrations are going to significantly affect that pH value. So this is how we do strong-weak titration procedures. Now I do want to point out, guys, that notice we did the titration of a weak acid with a strong base. If we flipped this process over, our curve would obviously be inverted, and our calculations on the front end would be based on Kb values and subsequently Ka value, and then the H plus ion concentration. So make sure that you think that process through before you proceed with calculations where the titrant is a strong acid and the thing being titrated is a weak base. So I'd like to look at a few differences between the pH curves of a strong titration versus a weak strong titration. And notice, guys, I'm talking about strong acid, strong base situations. The reverse would be true if we were titrating a weak base or a strong base. Okay, so I want you guys to notice initially the pH curve. Okay, the pH values at the strong example are going to be lower initially than at the weak strong, and the reason why is because the strong acid is going to ionize more completely, giving you more H plus in solution than the weak acid, and so your pH should be a little higher on the weak acid end. The other thing I want you guys to look at is the equivalence point. So your equivalence point for strong titrations is always going to be 7. Because when you produce that salt and the water, the salt that you're producing doesn't contain ions that behave as acids or bases, so water ionization is the determining factor for your pH here. In the case of a weak acid strong base titration, you end up with an equivalence point that's going to be higher than if this was a strong titration, and that's because the conjugate base that's produced from the ionization of the acid at the equivalence point will behave as a base and affect the pH in this way. Okay, so the other things I want to talk about, guys, are some of the other differences we see before we reach the equivalence point. Okay, so in the case of the weak acids, guys, the pH is going to increase more rapidly at the start, and then it starts to level off as you get closer and closer to the halfway point. And the reason why here, guys, is because we're reaching basically buffering setups because we're producing an anion from our acid that can behave as a base in solution. And so those changes are going to be less and less drastic as we have more of a buffer that's being created. Okay, and then after the equivalence point, guys, you're going to see similar changes for both the strong and the weak examples, because basically hydroxide ions are going to be the ones that are controlling the pH in both of those cases. Okay, so just be comfortable with this, guys. Also, please think this through in terms of if we were to do a strong base or weak base as the thing being titrated, and strong acid and strong acid as our titrant. Okay, so think those through, look at how the curves would appear, and get comfortable with that.